So thank you so much. It's really fun to have a conference in person. I actually changed a little bit my title to talk about something more recent. And what I'll talk about is mainly sort of the feedbacks between cell fate and tissue curvature that occurs in both directions with both of the stories I'm going to tell you have in common that they sort of appeal to, that they couple the two via collective tissue mechanics. So one of the things that sort of is quite clear when studying biology, right, is that we're not quite spherical cows. And one of the big difference, and unfortunately one of the big difference we have with spherical cows is that we have interesting shapes. And I think it's something you've probably all seen already, these kinds of pictures from Darcy Thompson's book. The left one is actually the cover of most edition. And one of the most interesting things, right, in his book is, and the thing that publicizes this the most, is the incredible beauty of shapes that emerge during in development. And in particular, one of the things I want to talk about today is the question of curvature, which is clearly something that you see in both of these examples. On the left is clearly it's logarithmic spirals with interesting properties. And on the right, this idea that Darcy Thompson had that you can sort of more or less go from one species of fish to another by dilating space or applying some type of curvatures to the field, with the idea in mind that you could try to explain the diversity of shapes through simple mathematical transformations. Of course, I mean, this is quite elegant as an idea, right? It's almost like Play-Doh and sort of playing with organisms by shearing them. Often the reality is not as simple, of course, and in particular, it's easy to get sort of trapped by the beauty of these things and trying to I mean, this beautiful mathematical picture is sometimes complexified by the quality of the data and the actual reality. I like this comics from SMBC Comics. You know, it's easy to see. It's easy to see things like golden ratio or fractals everywhere if you don't do really quantitative biology, right? And sometimes it just can be explained that by much more mundane explanations. And so what we have, the big advantage, of course, since Darcy Thompson has been that actually we try to use these words, these mathematical words, a bit more carefully and a bit more in a data-driven way. And in particular, I think what's been exciting in the past decade is to not just make this kind of geometrical transformations, but actually study the actual mechanical forces and the actual cellular mechanism that can explain this kind of sort of shearing transformations. With the idea, for instance, that mechanical forces created by the cortex can explain a lot of these deformations. And actually, it's great because I gave a beautiful talk, and so many of these concepts. He already introduced beautifully, so I will be able to go a bit faster on this. So this is a picture, right, where you imagine that these cells are generating forces and are shaping tissues in that way. But what I really want to talk about and give rise to sort of complex shapes and complex geometries. But one of the things I want to talk about is that is also a little bit the reverse feedback, right? That not all cells are equal. In particular, most tissues are partitioned into compartments of different fates. So this is an example, for instance, here of the intestinal crypt, where you see some stem cells are in the bottom and differentiated cells are in the top. And in a way, one of the things that you want to ask with this kind of pictures is the reverse feedback, right? Of how do stem cells know where to be and what they should do. Based on based on which cues can they actually adapt their fate choices to actually give rise to these complex organisms. And very broadly speaking, if you ask what defines a given cellular fate, in strong analogy actually with what also Hervé talked about in development, you can see about sort of two schools of thought. One, which is a more cell-centric hypothesis, essentially where you have some intrinsic regulation of fate via some biochemical pathways, where you see a certain fate as an attractor of the system, and its biochemical reactions. And another view, which is not of course mutually exclusive, which is more one of collective regulation, where what matters is the microenvironment, and fate emerges through some mechanochemical interactions between many cells. And so these two things, these two explanations are of course valid and interesting. There's one third thing that I think is a bit less considered, which I want to talk about today, is that if you go back to this picture of the crypt, the stem cells right here are residing in the regions of highest curvature and of curvature of a specific sign. And it's actually, in a number of settings, you can see that there's a pretty striking correlation between the fate of a cell and the local geometry and the local curvature of a tissue. And of course, one of the things I want to strike in the talk is that it's very hard from that kind of pictures to know cause and consequence, right? Because different cell fates have different mechanical properties, and so you could imagine that they create their own curvature. But that's probably not totally true, because there's a number of in vitro settings, for instance, where you can impose the geometry of the substrate, and you can see that fate actually adapts to the local curvature. So the central panel here is a marker for human epidermal stem cells, which correlate very well with the curvature of the dermis epidermis boundary, which also holds in vitro, and also this recent paper, for instance, by Matthew Lutoff, which is exactly these intestinal crypts, but where they impose the geometry of the environment, and you end up with your stem cells with a green marker here, which reside exactly in the regions of highest curvature as in vivo. So that tells you somehow that it's not just about sort of fate creating shape, and there has probably to be other types of feedback. But again, now with this kind of once you start saying this kind of question again, you end up pretty quickly with problems of cause and consequence, right? Because again, fate can change mechanics and geometry could conceivably change it back. And so as a modeler, it's a bit of a daunting task, right? Because each of these modules have quite a few parameters, and as soon as you start considering possible feedbacks, things get out of hand pretty quickly, and the parameter space explodes. And so what I want to talk about today is essentially start from minimal models, essentially soft matter inspired models where we start from first physical principles, and we want to ask what are the kinds of features, what are the kind of feedback that you almost get for free without putting some complex ingredients. And so the two stories I'm going to talk about is essentially the first one sort of linking fate to geometry, and the other one linking geometry to fate, before trying to wrap it up in the concluding slide. So the first part is a really fun collaboration with the lab of Prisca Liberali, and in particular the work of two great postdocs, Tutan from her lab and Cholet from mine that did the theory. And what Prisca had shown previously and beautifully on intestinal organoids is that intestinal organoids can start from just a monolayer where every cell is the same, and you get a first symmetry breaking event in a dish, where essentially you start generating a specific fate here, which is and then this which occurs essentially when things are rotationally symmetric, and then symmetry breaking in shape comes afterwards symmetry breaking in fate, which is a good system, therefore, to ask how does fate coordinate the acquisition of the final geometry of these intestinal organoids. And again, the interesting things about these organoids is that you end up with a crypt here where the stem cells are, which is the most curved region, which looks very much like the kind of geometries that you actually get in vivo. So the first thing that Tutan did is to actually image live. That's the power of this organoid technology, right? You can actually look at what's going on throughout symmetry breaking. And you can start here by seeing that initially you don't really know, you couldn't really tell where are your stem cells, right? Because things are pretty symmetric. But there's, if you look at a movie, you see a pretty dramatic change in shape towards the very end. If I make it a bit slower, right, you see on these red arrows that you see a crypt emerging, and there's when she was quantifying this, there's essentially two things that show up. One, which is that the crypts undergo apical constriction, which is actually something that's probably one of the most classical morphogenetic module. And had been shown before, but then there's also something quite interesting, which you might have seen, is if you look at the volume of the lumen volume of these organoids, so the volume of the lumen here, which is in orange, you see that morphogenesis coincides with a drastic reduction of the volume. So here you see they start shrinking by quite a bit, and then suddenly already it's not so clear anymore what's going on, right? Because you can imagine something like apical constriction, which is intuitive, but you could also see it as a football that you're deflating, and essentially as a buckling instability, right? And so to try to really now get to the quantitative aspect of this, we really needed to sort of understand it from a physical perspective, and understand sort of and go to physical models to understand the different forces. And one of the things that was fun to us is that if you start putting the two ingredients I told you are basically apical constriction, which is having a spontaneous curvature. It's a cell that wants to have a specific curvature, and changes in volumes. This is actually something that physicists in soft matter have been looked at quite a bit in the context of lipid vesicles. So this is actually a PhD work by Frank Jellischer, where if you take a lipid vesicle and you put a domain of spontaneous curvature in red here, you get a so-called budding instability, where when you reduce the volume, you have a transition where this thing closes because that's what minimizes the overall energy of the system. And so what was interesting to us is we thought, okay, this is something happening at a completely different scale. This is like multicellular instead of just lipids. But are there some similarities between these two processes? And so what Cholet did is to write essentially a simple physical theory of these organoids by considering the two domains of stem cells and differentiated cells, which have different mechanical properties, and by using a really minimal model, which is essentially a model considering that the energy of the tissue and the configuration just comes from a minimization of surface tension, very again similar to what Hervé introduced in the past. And so the general idea is, okay, let's try to say that probably these stem cells and differentiated cells have different tensions, but they're also coupled by the fact that they enclose a set volume. So therefore, if the volume changes, that's going to affect quite non-trivially, that's sort of a global constraint that's going to affect the overall morphology quite drastically. And is this exactly the same as lipids, or is it different? And it turned out that actually there are some things which are shared and some things which are novel in there. And so to cut a long story short, basically what we found in a back and forth between theory and experiment is that there's essentially a division of mechanical labor, where actually the spontaneous curvature comes mainly from actomyosin relocation that comes from the stem cells. So the stem cells relocate myosin apically and want to have a spontaneous curvature. And actually these changes of volume are taken care of by the differentiated cells, which stops absorbing some fluid and swelling to reduce the volume. And so therefore, if you do now a morphospace of possible theoretical shape of these organoids, on one hand you have the osmotic, essentially the volume changes the osmotic contribution of the differentiated cells, which is on the right here. And here you have the apical tension, the spontaneous curvature of the crypt. And you can see that if you want to end up with this kind of shapes like in vivo, actually both of your contributions, greatly contribute and help, because by reducing your volume, you reduce the tension in the monolayer, and you make it much easier to bend it through apical constriction. And so this is a very simple example where domains of cellular fate directly translate into domains of mechanical forces, which makes sense to close a crypt. And the question we had is, okay, this makes the right shape, but does this shape have an interesting function? And one of the interesting functions that we had, the first thing we did is to verify actually this theory. I'm going to, again, this is actually published, so I'm going to sort of go relatively fast on this. What Yutan did is to measure a number of morphometrics in these organoids, measuring in particular the thickness of the different stem cell and differentiated cell domain as well as their curvature. And they could find that by plotting one versus the other, by plotting purely observable, so purely the radius of curvatures as a function of the different thickness of the organoid, you could collapse actually a lot of data of organoids of different shapes and sizes on a master curve, which was exactly the one predicted by this phase diagram, which again shows that even though many organoids look slightly different, have different aspect ratios, they collapse on some rather simple mathematical equation. The thing that interested us even more is something that actually doesn't show up in these classical lipid vesicle studies, which was something which was a bit surprising, which is this region of the phase diagram here. And why is it surprising? Well, if I increase my tension, I close my crypt, right? I go up here, that makes sense. I want to be curved. And then what you see is that if I'm here and I inflate, it sort of makes sense intuitively, right? That I'm inflating my balloon, and so therefore I'm stretching both of my differentiated cells in blue, and my stem cells in red, right? You go back to something spherical by swallowing it, which makes a lot of sense. Which is a bit surprising is if you go above a critical value of tensions, then you can increase theoretically your volume to infinity, and your crypt stays completely closed, actually. And the reason for this is actually makes quite a bit of sense, is that because by putting actomyosin on the apical side, you don't just increase the apical tension, you also change the overall resistance of the tissue. And therefore, because of that, you end up with a property where your crypt, because your crypt is stiffer, it actually makes energetic sense to put all of the deformations in your differentiated cells. And therefore, it's a really simple mechanism where you mechanically protect your stem cells by having differentiated cells which are softer on the side. And so you end up with this sort of quite nice robustness once you pass this critical point of tensions. Is that true? Well, Chutan is this cool experiment in collaboration also with Joe Chan in the lab of Takashi Hiragi, which was to take these early organoids, which are expected to be in this region of the phase diagram, and put a pipette and literally do the experiment of going in this regime of the phase diagram, essentially controlling volume to see if you can check the morphometrics. And what you can see is if you take an early organoid, your stem cells here are this side. What you can see is that you stretch everything, basically. Your monolayer, your organoid goes back to something quite spherical, and you stretch both stem cells and differentiated cells. However, if you take a later organoid, which you predict to be in this region, and you do the exact same experiment, you start inflating, and suddenly your crypt stays completely closed, and all of your deformation has been taken up by the differentiated cells here, which is exactly what you expect through this sort of mechanical protection by the collective mechanics of these organoids. This is qualitative. You can actually make it quantitative again. You can look at how the morphometrics change as a function of volume inflation above and below the phase transition, and again, you can collapse everything on top of some relatively simple master curve, which is also a more quantitative but important check of the theory. Okay, so this is the first slide, essentially an example of how you go from domains of fate to domains of curvature, and how this might allow some specific function actually to protect mechanically stem cells. But the other thing I wanted to talk about is again what I mentioned in my introduction, which is the fact that seemingly in vitro it seems like stem cells are also able to react to their curvature, not just create it. And here, this is a beautiful paper by the lab of Fiona Watt, which is to put epidermal human stem cells on curved monolayers like this. And so here, this is like the mountains, and here, this is the crest. And she looked at YAP nuclear localization. And what's very clear, I think, is that YAP is nuclear on the mountains and cytoplasmic in the valley. And this is a pretty sharp transition, right? And for me, this is rather remarkable because you see this is one cell here in green. So these cells are reading a pretty large-scale information, right? This is curvatures of hundreds of microns, and they're able to know their curvature in a really sharp domain pretty incredibly, right? And so this is actually something that's emerging, that this idea of curvotaxis, that cells are able to sense really quite large-scale curvatures, both in vitro and in vivo. Oops, sorry. And there's, again, a lot of data that shows that it can control migration, cellular shape, YAP localization, but also a number of differentiation and cell fate properties in vivo. And so the question I really wanted to ask was, how can cellular fate now adapt the reverse feedback to large-scale curvatures? And this is really everything I'm going to show in the second part is also a fun collaboration with the lab of Sylvain Gabriele in the University of Mons. And again, all the experiments have been done during the PhD thesis of Marine Luciano. And again, actually, Cholet, the same very talented postdoc, did all of the theory I'm going to show. And so what Marine and Sylvain looked at is a simplified, they developed hydrogels which could be modulated, where they could modulate curvature and amplitude, and they put simplified cell system, which is MDCK monolayers, and they found a number, and they found again a number of things which were modulated, such as cellular shape, nuclear shape, YAP localization, lamins proliferation, etc., etc. And the question we really wanted to ask on the theoretical side is how? How can you actually sense this kind of information? And again, one of the things that surprised us is we used exactly the same model as before, so a vertex model, so a model of just considering the lateral and apical surfaces tensions in cells. And so this is a side view where you impose where you have this computational monolayer in red, and you impose the basal side to be on a substrate of given curvature. And what the cells want is to minimize their apical tension here and their lateral tensions in red, both of these things. And one of the things that surprised us actually is that actually you almost, in any this kind of vertex models, you get for free changes in cellular shape based on curvature. And the reason for this is because of minimization of apical tension. If you imagine that your apical tension is infinite and lateral doesn't matter, then the minimization of apical tension is going to tell you that the apical surface is going to be completely flat and doesn't care about the modulation of the basal side. Which means that by controlling a single parameter, which is this ratio of apical versus lateral, you're going to be able to sense differentially the influence of the curvature in terms of cellular shape. And this always predicts that the cells should be thicker in the valleys and flatter on the mountains. Again, this is actually on the archive if you want to look at the detail of the data, but we looked at, Sylvain and I looked at quite a few different curvatures and amplitudes, and you could see exactly that the cells were always thicker in the valleys and flatter on the crest, and that this effect was weaker and weaker as you increased the curvature of the substrate. And that by picking a single value of the apical versus lateral tension, which was 1.6 here, you can get quite well, the lines here are fits and the points are data. You can get quite well both the spatial modulation of the thickness of the monolayer and also the overall thickness modulation, the trend of the thickness modulation as a function of curvature, of the local curvature of the substrate. So then you might say, okay, who cares, right? Why do I care about cellular shape being changed by curvature? Well, one of the things that was seen in the data and actually makes quite a bit of sense if you think about these changes in shape is that the curvature also modulates nuclear deformation. And that made total sense, right? Because if you imagine now that you have a large nuclei on top of this crest, it's like it's going to be squished. It's going to be squished on the top, and it's going to have quite a bit more space in the bottom right. And in fact, that's exactly what Marine was seeing. She was seeing very striking changes in the position, aspect ratio, and volume of the nucleus as a function of curvature. And so what we asked is, can we explain that just again from this kind of shape changes by now just adding a simple model of nuclear mechanics to this vertex model and essentially saying that I have my shape from my vertex model and I'm going to consider a compressible nucleus with an elastic nuclear envelope that tries to minimize its energy again on the background of this imposed shape. And again, not extremely surprisingly, you're going to predict, of course, in a model differential properties of the nucleus as a function of position. I'm not going to go through all of them. One of the examples, for instance, that you predict that your nuclei should accumulate in the valleys because that's where the cells are thicker, and so if you want to be less deformed, it's like having a soap that sort of slips, right? It tends to go in the regions where it's less deformed, and so it tends to go on the valleys. And so that's exactly what Sylvain and Marine quantified here. They looked at the offset of cells, sort of how offsets are the cells. Are they in the center of the cells, or are they towards the valleys? And you could see that they're systematically in the valleys with a sinusoidal dependency, which was exactly the one that was predicted again by this simple model. There's a few. I mean, that's a bit intuitive, right? You try to go where you're not deformed. There was a few sort of on the physics side, slightly more fun and counterintuitive things, which was in particular that if you imagine, for instance, where you don't have a well-defined multiple between the cells and the wavelength, it's actually not that easy to have all of your nuclei in one valley, right? Because some cells are going to be curved. I mean, going to be in one space. I mean, the overall shape of the monolayer is a bit complicated. Whereas, if you imagine, for instance, a very specific wavelength where you have 2 cells per wavelength, then suddenly you have a really simple minimization where every cell, every nucleus can get in the valley, and that's a really simple ground state. And so, in physics terms, you predict a quantization of the Mechano response as a function of specific wavelength, right? Where the specific wavelength is a function of cell numbers, where the response is going to be maximal. And actually, again, I'm not showing you the detailed quantification, but if you look at this data here, where there's 2 cells per valley, you can see that nearly all nuclei are accumulated at the very bottom, maximizing the Mechano response. Whereas when you have only 1.5 cell per valley here, the response is a lot more messy. Which is, I thought, rather slightly surprising sort of prediction from the data. And again, now in the last few slides, I just want to get back to cellular fate, right? Again, this is nuclear mechanics, but what does it have to do with what I talked to you about, which is cellular fate? Well, a very simple thing, right, is that if you look at recent beautiful work on mechanosensation, one of the things that was proposed on flat substrates is that one of the ways you can control, for instance, important fate markers such as YAP nuclear localization was just by the deformation of the nucleus, right? Here, right, if you flatten the cell, you're going to open nuclear pores, and that's going to make sort of YAP go in. But the cool thing, I mean, so what this predicted very generally, again, without, you don't really need sort of equations for this, right, is that what you predict in this theory is that if you don't say, well, maybe I'm not measuring directly nuclear, what if I'm not measuring curvature? What if, again, I'm using exactly the same kind of mechanism, and I'm using cell shapes as a ruler somehow of curvature through nuclear deformation? What you predict is that these nuclei here should be the most deformed, and so therefore should have YAP nuclear, and these ones here should be less deformed and should have YAP cytoplasmic. And actually, that's exactly what you see in a number of systems, which qualitatively suggests maybe that actually you don't really need a new mechanism of sensing curvature. Just by collective mechanics of cell shape changes and what's known of nuclear mechanics, you could essentially go there. And if that's true, that's the last slide. If that's true, you can try to compare. You can try to make a master curve, which is your YAP to nuclear to cytoplasmic YAP ratio as a function of nuclear density, and you could try to populate this curve with different densities, uniform density on the flat monolayers, or different curvatures where differences in density emerge naturally. And if you sense YAP through your effect from flat monolayers on the nuclear deformation, you should predict that the dependency of curved substrates is the same as the density on flat substrates. And actually, that's quite similar to what you see, to what you see in the data, which suggests a really, really simple mechanism for large-scale collective sensing of curvature through emergent collective mechanics of epithelia. I think I'm basically done. The last concluding slide, basically, where we're interested in going, is now can we really? I've talked about on one side the feedback from fate to mechanics, and the other one from mechanics from geometry to fate. Of course, now we're a bit tempted to couple the two, right? In particular, in this kind of phase diagrams of organoids, I've treated these two things as completely separate: the apical tension in a crypt and the reduction in the volume as completely separate. But now, if you think about, for instance, changing in volume, you're changing in volume of the differentiated cells that are going to change your curvature of your crypt. And so, in principle, you could imagine you could imagine a feedback between the two, where the cells talk mechanically to the different cell compartments feedback to each other via changes in curvature. And essentially, we get some. It's very preliminary, but we get some interesting kind of things where, for instance, you end up with closed crypts which are as an absorbing state. Because if you imagine, for instance, that changes in the curvatures are going to increase, for instance, the apical tension in the crypt. Once you start closing your crypt, now your crypt is mechanically protected, so it cannot change curvature anymore, and so you end up with having, for instance, a volume reduction that initially, through mechanosensation, closed your crypt, but then you're stuck there. But then you're stuck there and cannot go on the other side of the feedback, which could be a way, for instance, that you use sort of lumen volume as a controller of this transition. But then, as soon as you finish your morphogenesis, it becomes a completely irrelevant variable because your organoid is trapped into this this closed state, and so you end up with a key developmental, for instance, force that becomes irrelevant as soon as development is over. And that's basically the end of what I want to talk about. This is very preliminary. I want to sort of again acknowledge our great collaborators and also Cholet, a great postdoc soon on the market that did all the work here. Thank you very much for your attention.